Yeah, Dipti.
Starts.
Yes.
Yeah.
Okay, sir. So, very good afternoon and welcome to all the members in today webinar. So, today we are celebrating the National Science Day 2021 by joint coordination of IETE Varanasi Sub-Center and IEEE Photonics Society Student Branch Chapter IIT BHU Varanasi. So, today we have very interesting topic, that is Raman effect, the story of its discovery and its recent application in electronics, photonics, and communication by P.K. Basu, who is retired professor in IIT Institute of Physics and Electronics, University of Calcutta. So now I'm also welcome to Professor Samak Bhattacharya, also Dr. Santanu Das. Now I'm requesting Dr. Samak Bhattacharya, please say some words about the today webinar.
Okay, good afternoon, everyone, and welcome you all on the occasion of the celebration of National Science Day, commemorating the discovery of Raman effect. So I will tell you just one my personal experience, since I am an alumni of Radio Physics and Electronics department. So I got the chance to get taught by PK Vasu sir in my BTech as well as my master's days. And when I was in the final year of my MTech in 2008, at that time, I'm telling you that Raman laser was just I think in 2005 or 6, it was first come into into action. I think Basu sir can correct me if I am wrong. So that time, so he had told that narrated that story very well in our class. So I am telling you that what I can tell that in a very short way, that he's the perfect person to describe this particular topic in a very much easier way or in a lucid way. So without wasting any time, let me just request my colleague Dr. Shantanu Das to formally introduce Professor Basu to the audience.
Okay, so thank you, Dr. Bhattacharya, and a very good afternoon to you all the participants, respected Professor Basu. I'm talking about Professor B.N. Basu, and of course, Professor P.K. Basu. And thank you for joining us with this auspicious occasion of National Science Day. And let me take an honor to introduce Professor Prasanta Kumar Basu, who did his BSc in Physics from Presidency College, Calcutta. He's one of the most prestigious college over there. And he did his BTech, MTech, and PhD all from RPCU. Joined in RPC department as a lecturer in 1971. So it's Radio Physics and Electronics department. Hopefully you guys all know this very well. It's one of the famous department over there in Calcutta University. So after his retirement in 2011, he worked as a UGC BSR faculty fellow, visiting professor at IIT Kharagpur, and an investigator in an Indo-Taiwan project. So in his long career as a teacher, researcher, in a semiconductor field, and administrator, he had more than 130 publications. Just wow. And many conference papers, 2 books, 2 book chapters, and he guided more than 20 PhD students throughout his career. And this is really very awesome, sir. We are really getting inspired from seeing your background. So Professor Basu initiated an international conference series, Codec, and earned for the department title UGC Networking Resource Center in Physical Science, the first in India. He worked as a postdoctoral researcher in Belgium. He is a recipient of Alexander von Humboldt Fellow in Germany. He is one of the most prestigious fellowships in the world. Professor Basu also have Professor Basu also got first INSA Research Fellow, visiting professor in TIFR and McMaster University, Canada. He also got INSA Royal Society Exchange Professor in UK and visiting professor in Chung Cheng University, Taiwan. Professor Basu also served for 8 years as a member of EPSRC College, UK, to review their project. Currently, he is completing a book on semiconductor nanophotonics for Oxford, UK, and revising the book Silicon Photonics for YU UK. So, with all this, I think your biography is quite often super impressive, and I would like to request you to take over the session and please give us some overview on this Raman spectroscopy used for communication and electronics.
I would like to add something. I'm
Please,
Bien Basu. Professor P.K. Basu was my classmate at
wow.
the Institute of Radio Physics and Electronics. It was a very
already known to everybody.
was it? Okay. Thank you. Okay. Thank you very much. Thank you.
Okay. First of all, I would like to thank IETE Varanasi section and Photonics Society, IEEE Photonics Society student branch of IIT BHU for giving me this opportunity to share my knowledge of C.V. Raman, his discovery, and recent applications, which is relevant for electronics and communication, that is current electronics, photonics, and communication. So with that, once again, I thank you, and let me start my talk from the beginning. You all know that the title is Raman Effect, the story of its discovery. I shall spend much time in discussing the story and the involvement of Calcutta University and its application in electronics, photonics, and communication. So, an authentic book is by G. Venkata Raman, Journey into Light, that was published by Indian Academy of Science and Indian National Science Academy. It's a very big volume, and I also read that it contains very interesting stories, and some of the stories I would like to share with you. But let me first introduce you to the scientific career of Chandrasekhara Venkata Raman. So these following slides have been taken from the Pure Physics Department website of University of Calcutta. This is prepared, these slides are prepared by Gautam Gangobadhyay, who is a faculty of the Department of Physics, and they published an article, Gautam Gangobadhyay and Anirban Kundu, during a conference organized by Pure Physics Department. So let me give you some idea. First, you must know the beginning of the University of College of Science. You know the Calcutta University, Madras University, and Bombay University. These three universities were founded in 1857, but initially the university was an examining body, conducted examinations, and Bankim Chandra Chattopadhyay and Jadunath Basu, they are the first recipients of BA degree from Presidency College, Calcutta University. However, then things evolved, and postgraduate classes in physics started in Presidency College from 1886. Acharya Jagat Chandra Basu and Prafullo Rai, they were the teachers there, and Satyendranath Basu, Meghnad Saha, P.C. Maulanavis, they were all students of these two stalwarts in physics and chemistry. However, the University Act changed in 1904, and that act allowed universities to accept private donations, to appoint professors, and to start new courses. And things begin to change when Sir Ashutosh Mukherjee became the Vice Chancellor. You know Sir Ashutosh Mukherjee, just like Acharya Madan Mohan Malviya of Benares Hindu University. He became the Vice Chancellor in the University of Calcutta in 1906 and started postgraduate classes, first in Sanskrit, Arabic, Persian, Pali, English, history, etc. By 1912, then he thought that he should start the science and applied science courses in the Calcutta University. So he asked his colleagues, Sir Taraknath Palit and Sir Rajbihari Ghosh to make donations, but there was one stipulations that the endowment should be not from ancestral properties, but from their own earning. So Taraknath Palit donated nearly 15 lakhs and his house in 35 Baliganj Circular Road, which is now as Baliganj Science College. And Palit endowment created professorial chairs in chemistry and physics, provided research fellowship for working in the university as well as abroad, and set up laboratories. Also, donations came from Sir Rajbihari Ghosh, and Sir Taraknath Palit and Rajbihari Ghosh, they are well-known barristers. So they earned a lot, and they donated, Rajbihari Ghosh donated 10 lakhs and created 4 professorial chairs. So it started from 27th March 1914. The foundation stone of the Science College was laid by Sir Ashutosh. Later, Ghosh made another endowment of 11.5 lakhs, and with that endowment, the Applied Physics Department and Applied Chemistry departments were created in the department. The condition was all the chairs were to be filled by Indians, that is, persons born in Indian parents. And well, I do not read this out. And as I have already told, that from this endowment fund, there were provisions for research scholars, research assistants, and assistant professors. As acknowledged by Sir Ashutosh, the donations were not from the ancestral properties, but from money earned by these 2 distinguished barristers themselves. So imagine, in 1912 to 1915, they donated nearly 30 or 40 lakhs, and also provided some space for creating building. So this is the story of first Palit professor, and you recognize he is Sir Chandrasekhara Venkata Raman. Well, when he was selected as the Sir Taraknath Palit Professor in Physics, Mr. C.V. Raman M.A., the governing body noted that, I read this out, Mr. C.V. Raman had a brilliant career in the University of Madras and is now an officer in the Indian Finance Department. His first paper on unsymmetrical diffraction bands due to a rectangular aperture was published in the Philosophical Magazine in 1906, while he was still an MA student. Since then, he has been steadily engaged in research work, which has latterly been carried out in the laboratory of the Indian Association for the Cultivation of Science. I may mention that his headquarters was in Calcutta, and he became interested in the work of in the activities of IACS, Indian Association for the Cultivation of Science. His investigation on the theory of vibrations and on optics, which have attracted considerable notice among European physics, are embodied in 22 papers, of which 7 have been published in the Philosophical Magazine, 3 in the Physical Review, 6 in Nature, and the remainder in the Journal of Indian Mathematical Society and the Bulletin of the Indian Association for the Cultivation of Science. In 1913, University of Madras awarded to Mr. Raman the Maharaja Iyengar Fellowship for physics. So I give you some idea about the research assistant who were independent. Shishir Kumar Mitra, founder of our department, he published independently. Emin Shah and S.N. Bose all worked as his assistant. They published independently. Only you can see that C.V. Raman and Mr. P.N. Ghosh, I am coming to P.N. Ghosh a little bit later, you have joint publications. So that's the story when he joined in 1917, but still he worked in Indian Association for the Cultivation of Science. Founded on is a picture of Dr. Mohendralal Sarkar. He was an allopath converted into homeopath, and he was a family physician or private physician of Sri Ramakrishna Paramahansadev. That was the building, old building of Indian Association for the Cultivation of Science in Bowbajar Street. And this association was established by Dr. Mahendralal Sarkar on July 29, 1976. And here Raman worked with his students. So I give you some interesting facts before presenting to you the first paper or the breakthrough paper. But before that, let me mention P.N. Ghosh, I mentioned that, and S.K. Mitro, they were Palit assistants of Raman, and both of them became head of Applied Physics Department in 25 and Radio Physics Department in 1949. Raman effect was discovered on February 28, 1928, where I had a confusion. Was it in Science College or in IACS? And later I verified that it was in IACS. I am coming to that a little bit later. Raman was so confident of getting Nobel Prize that he booked 2 tickets for Stockholm in ship nearly 6 months ahead of 10th December 1930. So he missed 1928, 1929, but he was confident that in 1930 he is sure to get. Why 2 tickets? Second one for his wife Lokasundari. Do you think Raman treated women equally? Answer is no. When Raman was about to enter Lokasundari's house for interviewing her for possible marriage, Lokasundari was singing a bhajan with words, Raman, Raman, offering devotion to Lord Rama. Raman thought it was for him, and that pleased him too much, and he decided to marry her. This is not my story, my Cook's story. You will find this in Journey into Light. That was written there. Raman never allowed female students in Indian Institute of Science when he was the director. Later he changed his stance a little bit. He was very much egoistic. Read Venkata Raman's book for constant tug of war between his group and the groups by Saha. Well, forget about Bose, Shama Prasad Mukherjee et al. Over control of IACS, and read many other interesting stories in Journey of Light. His nephew S. Chandrasekhara, who was also a Nobel laureate, chose not to seek his guidance. Still Raman is Raman. So with this interesting stories and the interesting stories related to his character and his personality, I just wanted to bring this into your notice. Now look at the paper which created history. It was published in Nature London in 1928, a new type of secondary radiation. And this don't want to read this out because we were recording and these are available to you. So if you find time, read that because time is limited. I come to the second page. It is sent as a telegram. The authors are C.V. Raman and K S Krishnan. What's the address? 210 Boubaja Street, Calcutta, India. Sent on 16th February by telegram. Remember, it was sent by telegram and no mention of IACS, but it's implied that Indian Association for the Cultivation of Science was the, he wanted to mention. No Calcutta University. Now, I just found only yesterday this paper, C.V. Raman's loyalty with the IACS, and is written by famous historian of science Rajinder Singh, appeared in Science and Culture in 2017. In conclusion, I just use this, do not want to quote the everything. In conclusion, it was written, Raman, who spent about 25 years of his life at the IACS, had true feelings for the association. One can say that he almost betrayed the University of Calcutta, which gave him livelihood from 1917 to 1932. In 1932, he joined Indian Institute of Science as his first director with double the salary of Palit Professor. Now the question is, who first coined the term Raman effect? Raman made the announcement in Bangalore on March 16, 1928, which was immediately published in Indian Journal of Physics. He then dispatched a preprint of the paper to Niels Bohr. He wanted leading physicists to know about it at the earliest, since he was aware that scientists in Russia and France were also working in this field. And I would like to mention that in different countries, this Raman effect is named as Mandelstam-Landsberg effect. In France, this is called Smekal effect and all that. The news of the discovery was also announced in Indian newspapers like Amritabajar Patrika, Kolkata. Sarkar, one of the students of Raman, 32 students of Raman working in IACS, later recalled that even in the middle of 1928, neither Raman nor his students made an effort to investigate theory of the effect. The effect was being called modified scattering. In June 1928, German physicist Peter Pringsheim, who performed independent experiments with benzol, toluene, and carbon tetrachloride, found spectra similar to the ones reported by Raman. Pringsheim published the results in a scientific journal, Naturforschung, and it was he who coined the term the Raman effect or the Raman effect in his paper. And this is taken from the article Rajendra Singh, S.C. Sarkar, Sushoman Sarkar, the witness of the discovery of the Raman effect, published in Asian Journal of Physics. Now, with these stories, I come to the technical part. Question is, what is Raman effect? I will try to answer this in very simple terms so that people can understand, but those who are more familiar or those who are experts, they can explain this in a better way. Just in a very elementary way, I want to introduce the Raman effect. What is Raman effect? In that connection, I have to mention some earlier work which are known as Rayleigh scattering, Stokes scattering, and anti-Stokes scattering. First thing, a beam of light incident on a small particle or a material having non-uniformities is scattered in all directions. If you shine light in some particles, then you get scattered light, maintaining the original wavelength. This is Rayleigh scattering. It's involved in this, included in most textbooks. Stokes in 1953 showed that in addition to the original incident light, there would be another emitted light having a wavelength higher than that of the incident radiation. Wavelength higher, that is frequency smaller. The spectrum of the light with upshifted wavelength or lower photon energy is called the Stokes line, and there existed or exists another kind of line, that is a strange phenomena of anti-Stokes luminescence was also known, in which the emitted wavelength is lower than the incident one, that is frequency higher. The line is called the anti-Stokes line. Internal energy of the object is involved in these processes. So Raman and Krishnan didn't know, but the theory and the effect was discussed or described theoretically by using quantum mechanical arguments, and here are these quantum mechanical arguments. So if you consider any particle, any matter, be it solid, liquid, or gas, in fact Raman worked on gas and liquid, so there are different quantized energy levels, you all know, molecular energy levels, etc. This is the ground state, and there are many energy levels. This is one of the excited states. E1 is the one excited state, E2 is another excited state, and the liquid, molecules in the liquid or solid or any matter, they vibrate just like they are connected to each other like a spring. And if a particular molecule vibrates, that vibration is transmitted throughout the sample. So these are vibrational modes or vibrational waves. And you know, in subatomic physics or quantum physics, wave is taken as a assembly of particles, and particles were treated also as waves. I will give some examples. All these are familiar to you. So in any case, I will come to this later on. So let light be incident on this matter, gas, liquid or solid. So it lifts an electron from the ground state to the upper state. Sometime later, this electron comes from the upper state, goes to the ground state, and there is light emission. That emission is known as a Rayleigh scattering. The same energy, same wavelength, and same frequency, that is Rayleigh scattering. Two other possibilities are also there. A light is incident on the matter, on the material. So an electron is lifted from the ground state, goes to the upper state. After some time, it comes down, but instead of going to the ground state, it goes to one of these states, vibrational states. So naturally, you will find that energy is lower and wavelength is higher. So this is called Stokes line. And what about this difference in energy? This difference in energy is given up to excite the molecule, liquid molecule or gas molecule or even solid. I am coming to solid a little bit later. There is another possibility. There is a transition from one of these vibrational states to an upper state. And then when it comes down, it goes from this upper state to the lower state. And that is, if you compare these two, you'll find that the emitted light has higher energy, there is higher frequency and lower wavelength. That's true. And so it's called anti-Stokes line. So Rayleigh scattering, Stokes scattering, and anti-Stokes scattering, these are known to everybody, to every physicist and chemist for a long time. So let me explain this once more. That is, from ground state, you shine light with energy H/omega L. Omega L is the angular frequency of the light. It makes an upward transition, that is absorption. From the excited state, it goes down to a lower state, that is a Stokes emission. Energy is H/omega L minus vibrational energy, H vibrational energy. This is the extra energy, vibrational energy. And for energy conservation, this vibrational energy should be given up to the molecules to excite their vibration. And that is one picture showing simple Rayleigh scattering, Raman scattered light or Raman scattered light with Stokes line and anti-Stokes line. You'll find that intensity distribution, where the Rayleigh scattering light has a large intensity, the Raman scattered light, that is Stokes line and anti-Stokes line, have a very small intensity, 0.00001%. Very feeble light, and naturally you appreciate that what kind of precision and what kind of patience was needed to find this emission. That is that Raman scattering, Stokes line and anti-Stokes line. However, our subject will not be on liquids and gases. We shall be interested in Raman scattering in crystalline solids or amorphous solids, I'll say solid states. So the same story, same picture. You have a ground state and you shine light. There is absorption. It goes to the upper state, excited state. From the excited states, it comes down to a somewhat in a middle state. So the emission has lower energy, that is higher wavelength. This is called Stokes line. And the remaining energy is given up to the solid, and solid has some vibration, wave motion of molecules, wave motion for atoms. And in quantum mechanical terms, this collective vibration is, this lattice vibration may be thought as a collection of particles known as phonons. Compare this to photons. Electromagnetic wave is composed of photons. Similarly, lattice vibration is composed of phonons. So photons and phonons. An incident bunch of photons are absorbed. The excited state comes to the ground level by emitting a photon and a photon and a phonon. The photon energy is smaller and is called the Stokes line, and there is an excitement of the phonon. So this absorption and emission are there, and Einstein introduced another term. This emission, we call this spontaneous emission, or you have all read in your higher secondary textbook, but in your advanced courses in engineering or in physics, you have become familiar with stimulated emission, which was introduced by Einstein later years in 1917, and the theory was presented by Einstein when S.N. Bose gave the quantum theory of radiation, this stimulated emission. So here are these two stalwarts, Satyendranath Bose and C.V. Raman. Well, Bose worked as an assistant under Raman, but published independently. And Bose and Saha were not very much impressed about Raman because they considered him to be a purely experimentalist without knowing the theory. Any case, I won't go into these details, but look at this. When a controversy arose about photon spin. In fact, in his first paper, S.N. Bose proposed photon spin, and Einstein changed it into photon polarization, which he didn't like. But he was confident, and Raman, a paper by Raman and Bhagavantam in 1931 in Indian Journal of Physics on an experiment related to photon behavior, they used the concept of spin and mentioned that the existence of photon spin was made known to them by Bose himself in a private conversation. This paper by Raman and Bhagavantam on spin and Bose's idea remained almost unnoticed by scientific community. It's a tragedy for us. So this is not all. I have introduced Raman effect, Stokes line and anti-Stokes line. Now I come to the applications in engineering, and in that case, we must distinguish between two things. Whatever Raman observed and whatever people did after his discovery is spontaneous Raman scattering. That is a Stokes line and anti-Stokes lines. These were spontaneous. You excite matter and you get emission a little bit later. You get Rayleigh scattering, you get Stokes line, you get anti-Stokes line. But in 1962, after laser was invented, semiconductor laser and maser were invented, there was a proposal for the stimulated emission of Stokes line and anti-Stokes line, that is known as stimulated Raman scattering. What is that? Stimulated Raman scattering is described in this way. You have a nonlinear element, that is, with the intensity of light, the susceptibility or the dielectric constant changes not linearly, it changes non-linearly. So it's not polarization is not susceptibility into electric field, but polarization is susceptibility into electric field, the chi2 coefficient into electric field square, etc., etc., etc. So you have a nonlinear element. What kind of nonlinear element? I am going to give illustrations of that a little bit later. So what do? You use a strong light, which is called pump, a strong light, remember. And at the same time, you feed a signal, and that signal I am going to mention a little bit later. That signal is my voice or the picture or anything in communication. So the signal is weak, pump is strong, and when they mix up in this nonlinear element, if the pump power crosses a threshold power, then the signal takes out energy from the pump and becomes amplified, and naturally, in order to conserve energy, the pump energy should be depleted. So you get out at the output depleted pump and amplified signal. So that's the thing. And you write this as the signal, change in signal with distance with Raman gain, IP, that is the pump power, pump intensity, and IS is the signal intensity, GR is the Raman gain, and you have a threshold, that is threshold is quite high. And I give you an idea. Pump power at present is 1 watt. 1 watt laser power, and it is obtained by 6 laser diodes of 150 milliwatt. So that gives 1 watt of power. So the stimulated Raman scattering and stimulated stroke scattering, these are the subjects of our interest at the present moment in the application of electronics, photonics, and communication. So I come to first describe is special type of laser, which is known as silicon Raman laser. It's a discovery made in 2004 by Intel people. What is that? Why that discovery was necessary? That had been necessary in connection with very large scale integrated chips. And this is a story. This is a present time, and that was a problem. You know that in VLSI you have interconnects. That means you have to connect transistor with a resistor. You have to connect a transistor with a capacitor, or you have to connect make connections between transistor and transistors. So that becomes very complicated, and you know that this metal oxide semiconductor field effect transistor, these are, I heard only a few days back that this length is 1 nanometer now, and this is quite small even in 2000, early 2000 or late 1990s. And in order to make connections, you have to make different interconnects. That is, you have a interconnect, and then you have to have an insulator. Then these are another layer of interconnects, etc., etc. So you find that 6 layers of interconnect. These are copper or aluminum, and with these interconnects, you get these complex integrated circuits, very large scale integrated circuits. And so you can understand that how complicated the situation is. And copper, unfortunately, it cannot work. It's a very good conductor at low frequency, but if you go to high frequency or high bit rate, so to say, it offers resistance, inductance, and capacitance. So if you have RLC circuits, then the simple argument, everybody knows that if you have an RLC circuit, then the bandwidth will be very much reduced, and you cannot send much information or much large amount of data very quickly from one point to another point. So that's the problem with copper interconnect. So what is the solution? Solution is, why not use optical interconnect? What is optical interconnect? I'll come to that in connection with communication. Optical interconnect is, you have some ray of light, and if you use ray of light as the connecting medium, then these rays of light can cross each other. There is no interference. But here you find that if you use a conductor or copper conductor, then in order to avoid interference, you have to use insulator. So this becomes very, very complicated. So that's the problem. And people thought that we should replace electrical interconnect by optical interconnect. And what is optical interconnect? You have a transmitter, that is light transmitter that sends light. You have a medium, that is maybe free space, maybe some waveguide, and you have a receiver. The receiver is your detector. So by that way, you can transmit signal from one end to other end, and that you do in fiber optic communication. You do this in a very miniature scale in VLSI integrated circuits. But for that, you have to use, you need a laser to transmit light, to send a signal. So what kind of laser? You know that integrated circuits depend on silicon. So you have to have a laser on silicon, but it's not possible. Unfortunately, it's not possible because you know that there are inherent problems. But let me give you some idea. before explaining that, well, interconnect is ultimate aim is to use in very large scale integrated circuit itself, replacing copper interconnect in VLSI. But let's do one thing. Instead of that, as a first step, we use optical interconnect between cards in a computer. And then you can use this as fiber to the home. And that is a very hot topic even today. And you find there is a huge government funding. There is huge funding from different industries. And I mentioned this importance. IEEE Photonics Society holds annually Group 4 Photonics Conference every year. So these are some of the consortiums, government funded and industry funded projects going on throughout this world, and this gaining interconnect. So this is the evolution. In 2002, it was thought that card-to-card interconnect by using optical techniques can be was conceived, and in 2007 it was realized. Then in 2012, one chip to another chip by using optical interconnect, and finally maybe it's possible to have interconnect within the circuit itself, within the chip itself, or within the system itself. Okay, optical interconnect I mentioned. You all know. I will come to this a little bit later. If you use copper interconnect, bandwidth is 5 gigahertz. There is huge power consumption because of the I squared R loss. But if you use optical interconnect, then you get high bandwidth, that is 40 gigabit per second and then more. Relatively low power consumption. There is no Ohm's law of Joule heating. And you can use wavelength division multiplexing by using optical interconnect. So the problem is defined, but the problem is to get a laser on silicon. Unfortunately, silicon is the material for VLSI electronics, but it fails miserably when you want to have light emitting diode or laser because of the peculiar band structure of silicon. It's an indirect band gap material and it cannot emit light. There is some quantum mechanical considerations. So if you are interested, I will explain that, but just take this for granted that this is not possible for silicon. Silicon is a poor emitter. Indirect nature of band gap needs phonons for momentum conservation. Is some tricky terms. Large recombination lifetime limits modulation bandwidth, and linear electro-optic effect is absent, and cutoff wavelength is not 1.55. That is the wavelength used 1.55 or 1550 nanometer wavelength in fiber optic communication. And instead of silicon, you have these 3,5 compounds or quaternary compounds, indium gallium arsenide phosphide, for example, grown on gallium arsenide, that is costly. So this is an artist impression. Somehow we have to find out a laser which is grown on silicon. And that's the real challenge. And in that case, this challenge was accepted, and they thought that the Raman laser on silicon will be a real solution. And what is Raman laser? Well, I told about quantized lattice vibration, that is collective lattice vibration, which are called phonons. In crystalline silicon, the phonon frequency is 15.66 terahertz. Well, you remember this 15.6 terahertz. I am coming to the next slide. So what Intel people did, that was announced in Nature in 2005, they used silicon substrate, also silicon. This is a PIN structure. This is a silicon waveguide. They used a laser beam, and laser beam is made incident on this silicon sample, and because of that interaction, then you have some down conversion or up conversion, or Stokes lines or anti-Stokes lines, and that will give rise to the stimulated Raman emission from silicon, provided this laser beam is of high power. It exceeds the threshold. So if you can do that, then you can have some stimulated Stokes scattering, that is silicon Raman laser. So this is the scheme. And as you have said, forget about this. Pump is 1536 nanometer, right? Pump is 1536 nanometer. And this is your silicon sample, silicon waveguide is top view of the earlier slide. This is the three-dimensional picture. This is the top view. So the pump light is incident on this silicon sample. And there is interaction. And interaction, because of interaction, what will happen? You will get a stimulated Stokes scattering. So notice this, pump is at 1536 nanometer, and you get Stokes line, that is laser output at 1669.5 nanometer. And if you just make out this difference in terms of frequency, this difference corresponds to 15.6 terahertz. The same phonon frequency in silicon. So that's the first success. And naturally, there will be amplification in the silicon medium because of Raman scattering, Stokes scattering. But this is an amplifier. So you have to convert this into an oscillator, that is the self-sustained oscillation or a radiation, a self-emitting radiation. So you have to use two reflecting mirrors. Those who are familiar with lasers, you know that the amplifying medium where population inversion takes place, that medium is enclosed between two mirrors, and there are reflections, and by positive feedback, amplifiers are converted into a self-sustained oscillator. So there are reflectors, and from these reflectors, you get the laser output. So that's the success. So this is again another diagram showing the structure of silicon. Is the silicon waveguide, as I have shown. This one is waveguide, silicon substrate, there's an oxide, and well, forget about this P structure, N structure. There is a complicated effect known as two-photon absorption. You sweep, you give an electric field, bias electric field, and the electrons generated are quickly swept out. So again, the repetition of that picture, pump at 1536 nanometer and laser output at 1669.5 nanometer. The difference corresponds to 15.6 terahertz, the same thing. Again, you'll find that when there is no emission, no stimulated emission, initially when the pump power is low, but when the pump power exceeds threshold, then there is sharp emission, there is a rise of the Stokes emission. So this is called the threshold, and threshold is quite large, and you get the stimulated Raman scattering from silicon. That was the discovery. However, the problem is the structure, whole structure, as I have showed in earlier figures, the structure of silicon is 33 millimeter, 3.3 centimeter, and you are talking about a few nanometer. So how does it fit into your present VLSI technology? So that is described here. And finally, some changes were made. Some micrometer scale Raman silicon laser was described or reported in Nature in 2013. Its size is 10 micrometer, is quite small, but still not that small. But still research is going on. You are using quantum dot silicon in a microcavity or use photonic crystal, but I don't want to enter into those details. That is one application. So you know that Raman laser finds an application in VLSI, and still work is going on. I will come to describe the recent developments in the last slide. So another application is Fiber Raman Amplifier. The principle is the same. That means Now, instead of silicon, you have an optical fiber. And optical fiber means, you know already that there are different bands, but let me concentrate on the conventional band, that is 1515 nanometer. So what do? You shine strong light, that is pump light, then it makes a transition, upward transition from a lower state to the upper state. From the upper state, it comes down to a middle state, and the difference is energy is given up as a phonon, and it excites the vibrational mode of the medium, that is your optical fiber itself. And that is the Stokes line. So if the pump power exceeds threshold, then there will be the stimulated Stokes scattering or stimulated Raman scattering, and will get amplification. So that's the story, and that's the principle. And what is special about Raman amplifier? You know, those who are familiar with optical communication, you know that the amplifier used in undersea communication or even in terrestrial communication by using optical fiber, RBM dot fiber amplifier, which works nearly 1540 nanometer or 1550 nanometer, RBM dot fiber amplifier is used, but only 1550 nanometer. If you want to go to other wavelengths, what are other wavelength bands? I'll come to later. This RBM dot fiber amplifier will not do. You have to use another rare earth element like neodymium or rubidium or praseodymium, plasmodium, etc. To change this from one band to another band, from conventional band to another band. Now here you know the beauty of Raman amplifier. Any wavelength will do, provided you will get Raman amplification in any wavelength, provided you have the corresponding pump power. That's difference between the phonon frequencies. So this is the beauty of Raman amplifier. And now come to silica fiber. If you look at silica fiber, if you look at the vibrational frequencies or the phonon modes, you will find that the phonon mode occurs at 450 per centimeter. That is corresponding to some wavelength. I will come to that. Yes. So if your pump occurs at 1480 nanometer, then you will get amplification at 1550 to 1580 nanometer, because the amplification band is high. So it's the same thing, lower wavelength, higher wavelength is a Stokes, stimulated Stokes scattering, 1480, 1580, and you make many things. You go to 1200, you will get 1200 plus this quantity, that is 130 nanometer. How much is it? And this 80 nanometer. So if you 1200, that will be 1280. So you have a wide choice. You can use any pump wavelength, and you can get any amplification in any wavelength. Why any wavelength? I will come to this a little bit later. The scheme is simple. The same optical fiber which is used in your undersea communication or terrestrial communication, you take that. Now you apply this is the input signal, that is the signal which I am wanting to transmit. That is, I am talking, I am sending a picture, or I am sending an information via my computer. That is the signal that is modulated, that modulates the light signal. So that is the modulated input signal is modulated in light signal. You apply a pump laser, so there will be interaction, and then the pump laser will be depleted, and you will get amplified input signal. So if you go to 1000 kilometers, then the optical signal will be attenuated, and you have to amplify this. So this is an amplifier, optical amplifier. So these are the features. Topological, simpler to design, no special doping is required. In RBM doped fiber amplifier, you need this optical fiber to be doped with RBM or neodymium or any other rare earth material, rare earth atoms. Here no special doping is required. The same optical fiber which is used in communication, that is used here, uses intrinsic optical nonlinearity of the fiber. Amplification takes place throughout the length of transmission fiber. Raman pumping is usually done backwards. You can make forward pumping, you can make backward pumping, and gain is higher at the receiver end of the fiber than at the transmitter end. So I come to define the different wavelength bands which is used in optical fiber communication. This is the attenuation characteristics of an optical fiber. And previously there was some spike, there was some peak due to the hydroxyl ion in optical fiber. Now the optical fiber has been refined, and you get a very flat attenuation curve throughout the range from 1250 to 1600 and beyond. Is quite flat. There is very little change in attenuation. You can see that there is very little change in the. So if you like, you can use the whole band, wavelength band. And I am coming to define this different wavelength band. This is the C band, that is conventional band, 1530 to 1565. That is used in earlier communication. And you have this short band, you have the extended band, you have the original band. Original band was used earlier, not when in the start of optical fiber communication. Then original band, then extended band, then short band, then conventional band, this long wavelength band, and ultra long wavelength band from 1260 to 1675. It's a long wavelength range or long frequency range. So you can utilize the whole bandwidth of the optical fiber to make communication from one place to another place by changing, of course, your laser wavelengths. Wavelength division multiplexing, you in wavelength division multiplexing, you use different wavelengths of laser, and thereby you extend the transmission capacity of the optical fiber. I guess you are familiar. Maybe I can give you an example. Say you have a highway. So what is done through highway? You transfer traffic, that is trucks, motor cars, etc., goes from one end to another end. Now in a highway, the traffic, the volume of traffic will depend on the number of lanes. Okay. So if you increase the number of lanes, then naturally you can carry more traffic through that highway. It's the same thing, that you have a highway covering from 1260 to 1675 wavelength and nanometer band, and these are different lanes. These bands are also divided into, say, 14 gigabit or 100 gigabit or gigahertz. So you can find that the number of lanes covered by this highway, super highway. So you can transmit more traffic through this super highway, optical super highway. So that's the beauty of Fiber Raman Amplifier, which is replacing the erbium fiber amplifier and semiconductor laser amplifier. What about a Raman laser? The same thing is you have Raman gain amplification. Now you enclose between two mirrors, that is two reflectors. You provide feedback and you convert an amplifier into an oscillator, self-sustained oscillator. So that's a laser. And instead of Fabry-Pérot laser, you use Bragg gratings here at this end, at that end. Is highly reflecting, but this is low reflecting output coupler, because unless if you have to make it low reflecting, light will be transmitted and will go forward from this end, from the left end to the right end. So that's simple. So you have this kind of two reflectors enclosing the amplifying medium, that is Raman fiber. So you get Raman laser. That is also in use. So I quote the current status of Fiber Raman amplifier and Fiber Raman laser. Today Raman amplifiers are widely commercialized devices. Almost every long haul, typically defined 300 to 800 kilometer, or ultra long haul that is typically defined about 800 kilometer fiber optic transmission system uses Raman amplification. On the other hand, nowadays commercially available fiber-based Raman lasers can deliver output powers in the range of few tens of watts in continuous wave operation. In addition, due to their tunability, compactness, and capability for multi-wavelength operation, fiber Raman lasers have great commercial potential in a variety of applications. This I have taken from Micromachines 2020 is the author, these two authors. They have discussed fiber amplifiers and fiber lasers based on stimulated Raman scattering, a review. So it's a problem for young electrical engineering. In electrical engineering, Raman laser is optically pumped, but in engineering, especially in communication engineering or electrical engineering, we don't like this optical pump. So we need everything should be operated electrically. So invent an electrically pumped Raman laser. I have searched, I didn't find much work. Well, only one work, but that is related to something else. But it strikes me, it's a very good problem, you find out. There is another effect which was discovered by Raman and Nagendranath in IISc or Raman Research Institute, is the acoustic effect. So is a Raman medium, say lithium niobate. You apply sound wave, ultrasound wave, ultrasonic wave by some transducer, and if you shine light, it gives us is diffracted into different beams, and that's the kind of modulation. You have much power and you have less power in this side lobes, side bands. So that's a kind of modulation. Is known as acousto-optic modulator, and modulator is, you know, is used in communication, in sending light or you changing the characteristics of light. So I come to the end. So let me summarize. Raman and his association with Calcutta University and Calcutta I have mentioned. Raman effect I have explained in terms of quantum mechanical transitions, Stokes lines and anti-Stokes lines, and different energy levels. Then I introduced stimulated Raman scattering and salient features. Applications of stimulated Raman scattering, I have taken two examples. One is silicon Raman laser, first silicon-based laser, which may find application in VLSI, still a research area. And naturally, second one is fiber Raman amplifier in telecommunication, that is finding application, and its volume production is there. I have shown you a picture of the device which is used. This device, Raman amplifier, is commercially available and used in optical fiber communication. So I have mentioned a little bit about acousto-optic effect, another thing which is used in communication, but don't like to elaborate on this because the application is still limited. There are other applications also in other engineering areas. Naturally, pollution, agriculture, water quality control is one of the applications, drugs and pharmaceuticals, because different materials and different chemicals, they have different vibrational frequencies and show different Raman features. So Raman effect is a versatile tool used in the study of materials, different chemicals, different pollutants, etc., etc. So with that, I conclude and offer my sincerest thanks to the organizers and to all of you who have listened to my talk very carefully and attentively. It's a pleasure to have interactions with you, and I feel honored that I have been invited to give this talk on this auspicious day. Thank you once again. Thank you very much. And well, questions, of course, I would like to answer if there are any. Thank you.
Yeah. Thank you, Professor Basu. It was a mesmerizing talk. And yeah, before I should continue saying something, I would like to request the participants, if they would like to ask some questions, or they have any questions, they want to interact, they have some discussion. So I can see one question in the chat box, but I would request the person who wrote it if he can start interacting, or else I can read it out on his behalf.
You may read it out. I don't know whether the
Please
part.
read it.
Yeah.
Okay. So the question is, recently 2 micron wavelength becomes an alternative of 1.55 micron. Can you use Raman amplifier in this wavelength?
Sorry, 1.55.
The question is, recently 2 micron wavelength becomes an alternative of 1.55 micron.
Oh,
Can we use
yes.
Raman amplifier in this wavelength? And this question is asked by Dr. Somabha Ghosh.
Okay, of course. Of course. I told you Raman amplifier is versatile. And L band, even L band or ultra the long wavelength band, that has been used instead of 1.5. We are going to higher wavelengths, L band. Of course, Raman amplifier can be used. The question is, you have to find out the corresponding laser. And so with the advent of Raman amplifiers, and its widespread use in fiber optic communication, there is a special industry which is termed as semiconductor lasers, of course. You prefer semiconductor laser as your pumping medium. There is already a specialized area of 14xx. XX means that corresponding to your wavelength, the corresponding laser, which would pump the optical fiber, 14xx. And I just remind you that I got an invitation from IEEE Photonics section, Photonics Society, Hyderabad. They are organizing 2 lectures today, which clashes with mine. There is one lecture by a Facebook gentleman who will narrate his story of using Raman amplifier in Facebook communication. And the second one from a professor in Indian Institute of Science. He has developed different Raman lasers and Raman amplifiers. So answer is simple, but I am not sure whether that laser has been developed. Naturally, people will try. The principle is simple. You just change your material and then you get a laser in that way.
Okay, thank you so much, sir. And the next question is from Saugata Chatterjee, and he's asking the basic difference between photons and phonons. And I think
Photons and phonons. Well,
basically a very preliminary question, but it's good.
I mentioned that. I repeat. Well, we are accustomed with waves, for electromagnetic waves. Okay, and when we look into light, we see from 2 different angles. One from wave point of view, which is used in microwaves, in some other communication, etc., etc. That is classical. And when we come to the interaction between light and matter, we changed our concept. We look into the particle concept, that is interaction between electrons and photons, interaction between photons and some other particles. Okay. Similarly, vibrational waves, which is present in all solids, liquids, and all that, they are, collective vibration. So when we consider in the classical sense, we talk about, say, sound wave, we talk about acoustic wave, we talk about pressure waves. But when we come to the interaction with subatomic particles like electrons, like even photons, then we convert these pressure waves or acoustic waves or anything into particles, and those particles are called phonons. So interaction, electron-phonon interaction, for example, is present when you find out the resistivity of a metal resistivity of semiconductor, right, or thermal conductivity, etc., electron-phonon interaction is involved. When we talk about Raman effect, this is photon-phonon interaction in terms of particles. So two ways of looking into things. One is wave picture, another is particle picture, and waves and particles are dual in nature, wave-particle duality. So that explains electromagnetic waves, photons, and vibrational waves, that is sound waves, mechanical waves, strain waves, pressure waves, etc., etc. These are termed as phonons. Is that explained?
Okay. Thank you so much for such nice explanation. And I hope so was happy that he got a beautiful explanation from a senior professor. So any more questions, please? Okay, so if somebody is writing, okay. No more questions, I think.
May I?
Professor Basu has a question.
Yeah,
Not
Professor
question.
Basu, please go ahead.
Not a question really. At 7 p.m., Professor Basu is going to deliver another lecture organized by Photonics Society. Am I correct?
Yes.
Yes, yes. You can mention the topic. The participants here can also join that program. Would you please tell the topic?
Topic is Narendra Singh Kapani, the father of fiber optics, and his missed Nobel Prize.
Yes. So
Oh, wow.
the participants, yeah, at 7 p.m. today.
Okay.
I'm going to attend it.
Yeah.
Okay. Okay. Participate. I'm going to participate. Yes. Thank you.
Okay, thank you so much. So if there is no question, so I'd like to invite Dr. Bhattacharya to just take over and give a big thanks to our professor, and then let us come to the end.
Okay, thank you, Dr. Das. And first of all, let me thank PK Basu sir for this nice presentation. It was really mesmerizing talk as mentioned by Dr. Das. Before I go for the formal vote of thanks, may I kindly request Professor B.N. Basu sir if you want to say something? B.N. Basu sir, you are mute, yeah.
Yeah.
If you want to say something, yeah.
What do you want me to say, please? On what?
On this particular talk, if you want to make any comment or anything, it will be great. Before I go for the formal vote of
yeah. Okay, please go ahead. Please, thank you very much. Thank you.
Yeah. So it's our honor that Professor Prasanta Kumar Basu had joined over here and accepting this talk on a very nice day of National Science Day of India. And incidentally, he has spoken about the contribution of Raman and his and basically the Raman effect on the particular effect in the electronics and the photonic communication. So let's thank Professor Basu for accepting the request. And also I request all the participants who are present over here, and we are also thankful to IETE Varanasi Subcenter as well as IEEE Photonics Society Student Branch Chapter for organizing this particular event. So with these words, I want to conclude this formal vote of thanks, and thank you, sir, for turning it up and for presenting this particular lecture.
Thank you all. Thank you all. Have a nice time.
Thank you so much.
Let's see. Let's hope that this situation improves, and we'll talk face to face.
Yes. We'll be very happy.
We'll talk face to face. Thank you very much. Bye. Have a good day. Good weekend. Thank you.